This is a video from section 4.4. The directions say find the limit. Use L'Hopital's rule where appropriate. If there is a more elementary method, consider using it. So let's go ahead and take a look at example 1. Suppose we had the limit as x goes to 0 of x minus sine x divided by x minus tangent x. Now, the limit is an indeterminate form of type, let me rewrite that, of type 0 over 0. Because as x goes to 0, sine of 0 is 0, right? So the numerator goes to 0, the denominator goes to 0. So it's an indeterminate form of type 0 over 0. So we're going to apply L'Hopital's rule. So this is the limit as x goes to 0 of the derivative of x is 1, the derivative of sine x is cosine x, the derivative of x again is 1, and the derivative of tangent x is secant squared x. Now, this second limit is still of indeterminate form of type 0 over 0. And so what we're going to do is we're going to apply L'Hopital's rule again. Because remember, secant of 0 is 1, right? So we have 0 over 0. And so this is the limit as x goes to 0 of the derivative of 1 is 0. The derivative of cosine x is negative sine x. So we have minus a negative sine x. So that's the top. The bottom is 0 minus, if I apply the chain rule, I get 2 secant x times the derivative of secant x, which is secant x tangent x. So let's go ahead and rewrite that on the next page. So we have the limit as x goes to 0 of sine x over negative 2 secant squared x tangent x. Now, what I would do, I would not do L'Hopital's rule on this line because that could get a little complicated. I would write tangent x as sine x over cosine x. So we have the limit as x goes to 0 of, now we leave the numerator alone, and I'm going to write the denominator as negative 2 secant squared x times sine x divided by cosine x. And then this is the limit as x goes to 0 of, we have sine x times cosine x divided by negative 2 secant squared x times sine x. But I want you guys to notice something. The sine x's can cancel, right? And then when I let x go to 0, I get 1 in the numerator, and I get negative 2 in the denominator. So the answer to this question is negative 1/2. And that's how you do the first example. So let's go ahead and take a look at example 2. Suppose we had the limit as x goes to infinity of natural log of x to the second divided by x. Now, this limit is indeterminate. Of type infinity over infinity. Okay, and so I'm going to apply L'Hopital's rule. And so this is the limit as x goes to infinity. The derivative of the denominator is 1. The derivative of the numerator is 2 times natural log of x, right, times the derivative of natural log of x, which is 1 over x. So this is the limit as x goes to infinity. Now, I'm going to write this previous line as 2 natural log of x divided by x. So I'm just going to slide that x over into the denominator. Now, this limit here is still of indeterminate of type infinity over infinity. It's still indeterminate. And so I'm going to do L'Hopital's rule again and say that this is the limit as x goes to infinity of the derivative of the numerator is 2 times 1 over x. The derivative of the denominator is 1. And as x gets large, 1 over x is going to go to 0. And so the answer to this is 0. And that's how you do example 2. Let's take a look at example 3. Suppose we had the following. Suppose we had the limit as x goes to 0 of e to the x plus e to the negative x minus 2 cosine x. So that's the numerator, and the denominator is x sine x. Now, this limit is indeterminate of type 0 over 0. This limit is indeterminate of type 0 over 0. And so I'm going to go for L'Hopital's rule. And so this is the limit as x goes to 0. Now, if I take the derivative of the denominator, remember I have to apply the product rule here. The derivative of x is 1, so I'm going to take 1 times sine of x plus x, and then I'm going to multiply by cosine x. Okay? The derivative of the numerator, I'm going to take e to the x. The derivative of e to the x is e to the x. The derivative of e to the negative x is minus e to the minus x. And then I'm going to take minus 2 times negative sine x. The derivative of cosine x is negative sine x. And so this is the limit as x goes to 0. And we get e to the x minus e to the negative x plus 2 sine x, right? Divided by sine x plus x cosine x. And this limit still has indeterminate form of type 0 over 0. And so I'm going to apply L'Hopital's rule again on this limit right here. Okay? And so this is the limit as x goes to 0 of the derivative of the numerator. We're going to do e to the x plus e to the negative x plus 2 cosine x. So that's the derivative of the numerator. And so I apply chain rule on this term here. The derivative of the denominator is, well, the derivative of sine x is cosine x. And then I have to apply the product rule on x cosine x. So I'm going to take the derivative of x, which is 1, and multiply by cosine x. And then I'm going to take and add x times the derivative of cosine x, which is negative sine x. So you really have to focus on one at a time, just so we're really careful. And so I'll put the answer up here, since I'm running out of room. As x goes to 0, e to the 0 is 1, right? So I get 1 plus 1, right? Cosine of 0 is 1. 1 times 2 is 2. So I get 1 plus 1 plus 2 divided by 1 plus 1. Because remember, as x goes to 0, this term is going to go away. And so here you get 4 over 2, which is 2. And that's the answer for example 3. So let's take a look at another one. We'll call this example 4. Suppose I had this one. Suppose I had the limit as x goes to 0 of x minus sine x divided by x sine of x squared. This limit is indeterminate of type 0 over 0. So I'm going to apply L'Hopital's rule here. So let's see what happens. So we're going to take the limit as x goes to 0. If I take the derivative of the numerator, I get 1 minus cosine x. The derivative of x is 1. The derivative of sine x is cosine x. If I take the derivative of the denominator, I have to apply the product rule. The derivative of x is 1, so I get 1 times sine of x squared. Then I'm going to take and add x times the derivative of the second, times the derivative of sine of x squared, and I get cosine of x squared. But by the chain rule, I have to multiply by 2x. So let's simplify this a little bit. So we get the limit as x goes to 0 of 1 minus cosine x for the top, and for the bottom, I get sine of x squared plus 2x squared cosine of x squared. And believe it or not, this still has the form, the indeterminate form of 0 over 0. And so I'm going to go through L'Hopital's rule yet again and take the limit as x goes to 0, right? Now, the top is 0 minus negative sine x. So I took the derivative of the top, by the way, right? If I take the derivative of the bottom, I'm going to apply the chain rule on the first term, and I'm going to get 2x cosine of x squared. And then I'm going to apply product rule on the second term. So I'm going to take the derivative of 2x squared, which is 4x, cosine of x squared, plus 2x squared, times the derivative of cosine of x squared, which is negative 2x sine of x squared. So this problem is long. Now, I can combine the first two, right, and call that 6x cosine of x squared. So let's do that. So this is the limit as x goes to 0. The top is sine of x. The bottom is 6x cosine of x squared. That looks like minus 4x cubed sine of x squared. And believe it or not, we have one more, okay, because this still has limit, this limit still has indeterminate form 0 over 0. So we're going to do the L'Hopital's rule one more time. And I know it's one more time because when I take the derivative of sine x, I get cosine x. And as x goes to 0, cosine of 0 is 1. So we're going to be done on this line. They're not all going to be like that, by the way. So we have two product rules here. So I'm going to take the derivative of sine x, which is, I'm going to take the derivative of 6x, which is 6, and I'm going to multiply by cosine of x squared, plus 6x times negative 2x sine of x squared. Okay. Here, we're going to make a little room here. This is going to take room. So let's write that on the next line. And we need a lot of room. So the derivative of the numerator is cosine x. And then I'm going to write 6 cosine of x squared plus 6x times negative 2x sine of x squared. So that's just the first two terms. Now I'm going to take minus, and then I'm going to do the derivative of 4x cubed, which is 12x squared, sine of x squared, plus 4x cubed times 2x cosine of x squared. So barely. Now, I want you to notice something. As x goes to 0, can we agree that cosine of 0 is 1, so that's going to go to 1? This term is going to go to 6. This term is going to go to 0, right? This second term, because sine of 0 is 0. So is this term. And if I plug in 0 here, this term is going to go away. The only one left is that first term. And so the answer here is going to be 1/6 before you have to simplify further. So that one was long. So, all right, let's do example 5. Suppose I had something like this. Suppose I had the limit as x goes to infinity of x sine of pi over x. Now, this one's interesting because this limit has indeterminate form. Of type infinity times 0. We don't know how to do that. We don't know how to do infinity times 0. That limit is not 0. So what I'm going to do is a little, perhaps you can call it a trick. I'm going to rewrite this limit as sine of pi over x, and I'm going to divide by 1 over x. So I'm using the fact that x is the same as 1 over x. Why? The reason why is because you want to get this limit in indeterminate form of type 0 over 0 or infinity over infinity. And that will allow us to apply L'Hopital's rule. Because if you notice, as x goes to infinity, the numerator will be 0, the denominator will be 0. Boom, we could do L'Hopital's rule. And so I'm going to differentiate the numerator, and you're going to get cosine of pi over x times the derivative of pi over x, which is negative pi over x squared. So we took the derivative of the top. The derivative of the bottom is negative 1 over x squared. Now, remember, a negative divided by a negative is a positive. So I could write this as the limit as x goes to infinity of x squared cosine of pi over x times pi over x squared. But the x squareds cancel, okay? And so this is the limit as x goes to infinity of pi cosine of pi over x. So the answer is pi, because cosine of 0 is 1, and pi over x will go to 0 as x gets large. So that's a really good one, and this is really the main idea there. So that's example 5. Example 6. Suppose I had this one. The limit as x goes to infinity of square root of x e to the negative x over 2. So I'm just going to rewrite this and get rid of that negative exponent because it's in the way. And so we get square root of x over e to the x over 2. And this limit has indeterminate form. Of type infinity over infinity. And so I'm going to differentiate the top and the bottom. Now, the derivative of e to the x over 2 by chain rule is 1/2 e to the x over 2. Okay? Now, remember that square root of x is the same as x to the 1/2. So let's remind ourselves. And if I take the derivative of the top, I get 1/2 x. By the power rule, it's 1/2 x to the negative 1/2. Because remember, 1/2 minus 1 is negative 1/2. But we can kill off those halves, right? And so this is the limit as x goes to infinity of. Now, I'm going to move that x to the negative 1/2 back to the denominator. just by changing the exponents to a positive 1/2. And then we're going to multiply by e to the x over 2. But as x gets big, this whole limit goes to 0. So the answer to this one is 0. And this is a good stopping point. This will conclude this video for section 4.4. We did 6 more examples applying L'Hopital's rule. Thank you.